Hi everybody, and welcome once again to another installment of our series of Discovery Seminar Talks. I am Matilde Mingozzi, a Space Telescope postdoc working with Bethan James and Alessandra Loisi, and today I will be the chair. The aim of these Discovery Seminars is to showcase the work of postdocs of the Space Telescope and Johns Hopkins community. Early career researchers, as you know, have been disproportionately affected by the COVID-19 pandemic due to reduced travel and networking opportunities. And on top of that, we have here a large community of international postdocs that have been separated from their families and loved ones. With these talks that will take place till the end of July, we want to provide a platform for these postdocs to show their results to an international audience of astronomers. And please, at the end of each talk, feel free to ask questions using the raise hand button. I will call on you and then you can unmute yourself to speak, or you can type questions in the chat and I can read them for you. Now I will introduce the first speaker of today, Mireia Montes. Mireia Montes did her PhD at the Instituto de Astrofísica de Canarias in the Canary Islands in Spain. Then she moved to Yale University for a postdoc, followed by another one at the University of New South Wales in Sydney, Australia. Since October 2020, she holds one of the Space Telescope postdoctoral fellowship, working on the low surface brightness universe. That is also her main line of research, and she will talk about this today. And she's also part of the HST WFC3 group. So please, Mireia, the floor is yours, and thank you.
Thank you very much, Matilde. As Matilde said, my research interest is in the low surface brightness universe. In particular, I study the intracluster light. But what are those things? So there are several surveys that have revolutionized our understanding of the universe. One of those, and probably the most famous one, is the Sloan Digital Sky Survey. At the time, and still now, you can see some papers being published with using this survey. You had a wide field survey in several bands of multi-wavelength that provided the tools to study the universe and characterize it in a statistical sense. However, the survey had several limitations, and one of them is the depth that it reaches. For Sloan, it's around 26.5 magnitudes per square second. That means that our knowledge of the universe is biased towards the objects that are brighter than that. So here's an example of the Sloan Digital Sky Survey. This is a galaxy observed by Sloan. And if we take deeper images than Sloan, you can start seeing all these objects around the main galaxy, and you can also see all this diffuse light. And this is what we call the low surface brightness universe. This is the universe beyond this limit, this 26.5 magnitudes per square second limit. It's beyond what Sloan was capable to study. This is a largely unknown regime due to the limited availability of imaging that is deep enough. There are a huge amount of astrophysical phenomena that are faint that can only be studied at low surface brightness. For example, you can study the zodiacal light to understand the solar system evolution. You can also observe the Galaxies series, that is the filaments of dust of our galaxy, to understand the properties of the interstellar dust. And you can also study the low surface brightness galaxies or dark galaxies to try to understand or try to investigate why the number of observed galaxies is kind of missing. So we are observing more. We are predicting more galaxies than the ones that we see. And of course, we have the clusters of galaxies. So these observations of clusters of galaxies have revealed a diffuse glow filling the space between the galaxies in the cluster. For example, we have here an image of the Virgo cluster. It's one of the nearest of our nearest clusters. And you can see that there is no end to the galaxy. So they continue. There's this glow that fills the space between the galaxies in the cluster, and basically it fills kind of all the image. This is what we call this faint and extended light, is what we call the intracluster light. So in the observations of clusters, we see that this light is concentrated around the brightest cluster galaxy, or BCG. It presents as an excess of light at large radius over the light profile that describes the galaxy. For example, here we have this profile in dark blue that describes the system, and we have here in light blue the one that the macros profile that describes the light profile of the galaxy. And this excess is what we call intracluster light. We also see that the ellipticity increases with radius, and in some cases there are sharp variations in the position angle of these ellipses. So these three things together, the excess of light, the ellipticity increases with radius, and sometimes that is this variations in position angle, these three things together tells us that the intracluster light is a separate stellar component. To actually know if there, if the galaxies and the intracluster light are different components, we need kinematics of the intracluster light. And for that, nearby clusters are the best place to study, because those are the ones that are close enough that we are able to conduct this type of observations. Either if it's like the spectroscopy of the integrated light, or using globular clusters or planetary nebulae as tracers of the stellar population. And here, so in these observations have shown that the velocity dispersion of the BCG increases with radius. For example, here we have the velocity dispersion of this cluster, of the Virgo cluster, and we see that it increases with radius until it reaches the velocity dispersion of the galaxies in the cluster. So basically, we can define this intracluster light, this component, as the stars that are not bound to any particular galaxy, but they follow the potential of the cluster. But where does it come from? Where does this light come from? So we come up again to this deep image of the Virgo cluster. In here we can see these streams here, and here that are basically feeding these intracluster light components. So in fact, this is the key of the origin and why we are interested in this field, in studying this light. So for what we've seen in clusters, we know that the intracluster light forms during the interactions between the galaxies in the cluster. So basically, it is a tool to see what happened in the cluster. We want to observe and characterize the intracluster light because it unveils the history of assembly of the clusters. Its fraction of the total luminosity of the cluster will give us the efficiency of those interactions, while the evolution with time of this component gives us an idea of the timescales of these interactions. However, observing the intracluster light, it's not easy. We normally only have we don't have the kinematics. We only have the imaging from those clusters of galaxies, and there is no clear transition between the BCG, between the galaxy and the intracluster light. So observers have to come up with different definitions to study the intracluster light components separately. So the most widely definition used, and the easiest one to implement, is to define astrophysical brightness cut. So that is basically that the light that it's fainter than a certain value, that has a certain threshold, is what we define as intracluster light. However, as you can see here, this is in the middle panel, this definition with this definition, we are missing all the light that is in projection to the, to the BCG and to the other galaxies. Another method that we normally use is to use two models, normally STScI models, to describe the light profile of both the BCG and the intracluster light, which is here, the panel C. And in here, we recover all this light that is missing in projection to the BCG, but we lose all the information of, in case of, asymmetries, of tidal streams, of light that is associated to other galaxies. But recently there's been a push for methods that can separate both intracluster light and galaxies for the whole image. Here there is an example of that. I call them the wavelength-like methods, as the idea behind them is kind of filtering these two components to keep the diffuse and extended component and get rid of all the like the tinier galaxies or other objects that are in your image. Well, once we can define the observation-led intracluster light, we can see how it correlates with different properties of the host cluster. In this case, we are interested in see how it evolves with time, as it will provide clues about the mechanism of its formation. And well, as you can see here, this evolution depends, and this evolution depends depending on how we define the intracluster light. When using astrofast brightness cut, which is the gray symbols that you see here in this plot, there's a clear trend of increasing intracluster light with decreasing redshift, so it increases with time. Especially, most of it being formed below redshift 0.5. However, if we use the same technique in simulations, which is this purple line over here, we see that this trend is more gradual. The same thing happens if we use these two models to describe BCG and intracluster light, which is the black symbols over here. We see that this evolution, this trend, is more gradual. So yes. Well, here you have a cartoon that describes like these different evolutions depending on how you define the intracluster. So yes, it seems that this component is evolving, but we need to find how to define it properly so we can understand how it evolves with time. When we look at how the intracluster light correlates with mass, there is no obvious correlation. However, we do not have a lot of data in the low mass regime, in the group regime, and the data that we have in the cluster regime is kind of noisy, so it kind of varies any information of any trend that we could see in here. But what we do know is what forms the intracluster light. So recently, it has been possible to study the stellar populations of the intracluster light accurately enough that we can begin to understand how this component forms. We have seen that there are gradients in colors and in metallicities that point to tidal stripping of massive satellites, of Milky Way-like satellites, as the dominant process of intracluster light formation. While disruption of total disruption of dwarf galaxies could create similar gradients, they cannot account for the total luminosity observed in this component. However, there are some clusters that show flat gradients, which means that the formation mechanism in this case might be related to major mergers, because they erase any gradients in the stellar populations. And that those stellar populations might depend, those stellar populations in the intercluster light might depend on the peculiarities of the cluster. And of course, you have to bear in mind that this is for integrated light, meaning that these properties are an average of the true distribution of the metallicities that are in the intercluster light. But one of the things that are more surprising and interesting of the intracluster light is its correlation with other properties of its halo. And here I will introduce these 6 fogs. These are the Hubble Frontier Fields clusters. These are some of the deepest images ever taken by the Hubble Space Telescope of clusters of galaxies. So apart from these gorgeous multi-wavelength deep images that you see here, the Frontier Fields Initiative also provided to the public maps of the distribution of mass of these clusters. So in the illustrious simulation, Quiles et al. 2018 found this very nice correlation between the mass of the system, the total mass of the system, and the slope of the stellar halo. In this case, for galaxies, the stellar halo, and for groups and clusters is the slope of the intracluster light. Using the observations of the Hubble Frontier Fields clusters, we showed that this correlation also held for very massive clusters, which are the masses of the Hubble Frontier clusters, so 10 to the 15 solar masses. And not only that, but in Quiles 2014 and in Quiles 2018, showed that these slopes are very similar to the dark matter slopes. So that is that the distribution of the intracluster light is as shallow as the distribution of the dark matter in clusters. So we had the deep observations of the frontier fields clusters, and we had the mass maps. So basically, we decided to compare both of them. So here I show the examples of 2 of the 6 clusters. So we compare the distribution of the intracluster lights, the distribution of the total mass of the clusters in the middle panel, and the distribution of X-rays, as they can be another potential tracer of how the mass distributes in clusters of galaxies. And we can see here that the intracluster light and the mass maps are very similar, while the X-rays are doing other things. And that is expected, but because these clusters are in the process of merging, so the gas that are in them is disturbed. So basically, we see that actually the intracluster light is a good tracer of the distribution of the total mass in this cluster. However, we were limited in this work. We were limited by the field of view of the WC3 camera, so we could only reach 140 kiloparsecs. But the simulations came to the rescue. This similarity between intracluster light and the distribution of dark matter in clusters was studied in the Sea Eagles simulations. These are some examples of the clusters in Sea Eagle, and we can see here that both stars that are in red and the dark matter that is in green follow each other very nicely and up to 1 megaparsec from the center of the cluster. So it seems that up to 1 megaparsec, we can claim that the intracluster light is a good tracer of the dark matter distribution in clusters of galaxies. And why is that? Why is the intracluster light such a good tracer? So we know that the intracluster light is an extended component, as the satellites in massive halos tend to deposit their stars at larger radius. We also know that, by definition, that the stars in the intracluster light follow the potential of the cluster instead of being bound to any galaxy. So these 2 things together naturally make the intracluster light a good tracer of the dark matter or the total matter distribution in clusters of galaxies. And this thing here, it has extraordinary consequences, as we can now basically use this basically we can see this distribution of dark matter with basically by only taking a picture. And if we know how the dark matter distributes in clusters of galaxies, we are able to constrain the properties of this dark matter. So this property of the intracluster light has already been used to measure something that is called the splashback radius in clusters of galaxies. The splashback radius is the radius where the particles, in this case stars or dark matter, reach the apocenter of their first object. So basically it separates material that is bound to the cluster to material that is falling into the cluster. So basically it's a physically motivated edge it's a physically motivated boundary for the cluster. So Dixon et al. In 2021 used the Sea Eagle simulations to detect this splashback radius using the light profile of the clusters. And this splashback radius show as a dip here in this red line, as a dip in the surface brightness radial slopes of the light. As you can see here in the dark matter, which is something that we already knew, but also this dip appears in the light profile of the cluster. A little bit later, the same year, Gonzalez et al. 2021 found a similar signature in their dedicated observations of the frontier fields. So they saw a drop in the surface brightness radial profiles, which showed as a dip, as this dip in the surface brightness radial slope that you see here in this black line over here. However, this signature is a little bit smaller in radius than the signatures that we see in the simulations, and that might be caused because this particular cluster is a very complex it's a very complex merger. So
Mireia, you have 5 minutes left.
Yeah, thank you. If this is confirmed, it will be the first identification of this radius in an individual cluster. So we have seen that intracluster light is a promising tool to study several things like the assembly of clusters. We can also use the intracluster light as a tool to kind of see the dark matter in clusters of galaxies, and consequently being able to study what is this dark matter, and being able to identify the splashback radius in clusters of galaxies. So there's still, as I've just seen in my talk, there's still a lot to discover in this field, and we still don't know what else the intracluster light is going to tell us. So if, and this is like more of a shameless advertising here. If you want to learn a little bit more about intracluster light, you could check my review that was published in Nature Astronomy a month ago. Thank you very much.
Thank you very much, Mireia. Thank you very much for the beautiful talk. I will applaud for you. It's nice that we have many people that are watching in different rooms. So if you have, I see that Mark Postman has a question. You can unmute yourself and you can ask.
First of all, Mireia, that was a great talk. ICL has always been a fascinating phenomena. I was intrigued by that last, the plot where you show the surface brightness falling off dramatically at about 1 megaparsec. Is there any concern that that's a subtraction effect from sky background, because you're getting to the limit of the detector, what the coverage was, and if you've not got the background sky exactly right, you would see something very similar to that?
Yeah, that is always like the sky background subtraction is always a concern in anything that has to be with loss of brightness. In this case, the observations were made. So you have the cluster here, and the observations were made with HST, kind of like in one direction of the cluster.
So
So
they have good coverage.
we were trying to reach like more than 2 megaparsecs, so we could have like the best sky subtraction, because of course there's when you are dealing with especially with intercluster light, the fact that it's extended, it means that in most of the cases you are over subtracting because you have intracluster light there. In this case, we are trying to reach as farther as possible to avoid that.
Okay, good. Thank you.
Are there other questions? You can type them in the chat. You can raise your hand with the raise hand button that is on the top right. You should click on people, and then on the bottom you see the button raise hand.
I'll have one more question if no one else does.
Yeah.
So
You can go.
you showed that one of the definitions of ICL is a deviation from the art of the 1/4 law, as excess seen at high cluster centric or high BCG radius. But BCGs have profiles that can vary significantly from art of the 1/4, and so I guess it's a convoluted question, right? How robust is that definition, or is the fact that we see the deviation indicative that more BCGs might have ICL than we think?
That is a concern, because depending on, you normally describe your galaxy with a STScI, and depending on, like your N, you can have more kind of wings, more halo than if you have like a smaller STScI, right? Here, it's not much of, you still have this excess of light, no matter like the STScI, because it's just the intercluster light is so extended. So at some point you see that it just there's like something that is remaining there.
Okay, cool. Thank you, and great talk. Really appreciate it.
We have a question in the chat from Stefan McCandless that asks, how do you define a radial profile for a banana-shaped object?
So yeah, that's a good question. It's basically defining like a radial profile of something that is very, very, that is basically like a very thin ellipsis.
Okay. I don't see other questions. I have a quick one, actually. We already talked about this, Mireia, several times. I'm not an expert about the topic, but what are the next, what are the next steps to discover more about the intracluster light? Like
So
with the new telescopes that there would be.
So the first one is trying to find like a definition that is kind of common, or because as you have seen in the plot that I've shown with Redshift, the definitions are they're all over the place. Like everybody uses the definition that they think it's most appropriate. But you have also like the evolution of the stellar populations and everything that kind of messes up this plot, this type of plots. So we need to have a definition that is kind of more robust to against like the evolution of the stellar populations, and having like something that actually we can compare. And the other things are we have like several surveys Well, several facilities that are being built, like the Rubin Observatory. We have Euclides, and in the future we will have the Roman Space Telescope. And I mentioned this particularly I mentioned Roman because that is gonna have a large field of view, which is gonna reduce like all this problematic of the effects of sky subtraction and things like that.
Okay, thank you very much. So I don't see other questions, but please reach Mireia, sending her an email, or if you are in the institute, going to her office to ask for to ask questions. And now we will move to the second speaker of today, Mitchell Revalski. So Mitchell obtained his bachelor in physics at the College of New Jersey in 2014. And then he pursued his PhD in astronomy, working with Mike Crenshaw at Georgia State University as an NSF Graduate Research Fellow. He is now a postdoctoral researcher working with Mark Revalski here at Space Telescope, where he focuses on ultra-deep studies of quasar fields using HST and MUSE, as well as continuing his AGN work. In addition to research, Mitchell enjoys public outreach and collaboration, so please don't hesitate to reach out to him with your ideas. And please, Mitchell, the floor is yours.
Thank you so much for the introduction. Just interrupt me if you can't see the slide deck or can't hear me. And thank you so much for joining everyone today. I'm really excited to kind of give you an overview of our investigations into the energetic properties of mass outflows in nearby active galaxies. So to kind of set the stage, many of us are interested in supermassive black holes and their galaxies and how they interact with the environments that they reside in. And so there's no better way to study this than study supermassive black holes which are actively interacting with their galaxies, which means we're going to be looking at active galaxies or active galactic nuclei. So we now have very substantial evidence that there's a supermassive black hole at the center of nearly every massive galaxy. And as we can see in this artist rendition, they can interact as material is funneled down into the nucleus. It is heated up and compressed in an accretion disk around the supermassive black hole, and this emits an immense amount of radiation, which can travel out into the host galaxy, couple with the interstellar medium, and drive powerful mass outflows away from the supermassive black hole. And we tend to see these outflows in kind of two main flavors. The first are these more wide-angle, slower gaseous outflows that we see in ionized and neutral and molecular gas. And then we have radio jets, which are these very highly collimated, more pencil beam structures that can travel at nearly the speed of light. And today I'll be focusing more so on the first kind of these types of outflows. Now, we're really interested in studying these in terms of their effects on galaxy evolution because it spans a very large dynamic range in spatial scales. So at the smallest scales, we see scaling relationships between the mass of the supermassive black hole and the mass and the size of the bulge of the galaxy. And even though the supermassive black hole has an immense gravitational pull, they're really not aware of each other on very large scales. And so this is some evidence that maybe these systems essentially grew up together by exchanging mass and energy. In addition, of course, if we're heating material up and we're moving it out into the further reaches of the galaxy, this could have big implications for the rate at which stars can form because we're evacuating those reservoirs of potential star-forming gas. And on the largest scales, particularly when we have those powerful radio galaxies, we can actually heat up gas that's in the space between galaxies within galaxy clusters, and that's going to affect the rate at which material can cool and recycle through galaxies on long time scales. And all of this kind of ties together to the formation of galaxy structure. If we don't include this type of mass outflow feedback in our models, then we tend to basically make too large of galaxies because we haven't had this feedback effect to essentially blow some of them apart. Now, one of the key difficulties in studying these outflows is that they're very multi-phase and multi-scale, from ultra-fast outflows very close to the accretion disk out to these more ionized, neutral, and molecular outflows within the scales of galaxies, out to these radio jets that can be on the scales of galaxy clusters. And so we need a lot of different multi-wavelength observatories to kind of piece together what's going on here. In our studies, we've chosen to focus on what we call narrow line region outflows. And so this is ionized gas that displays strong emission lines from the UV through the near IR. And we're particularly interested in these because they span basically the smallest scales that we can spatially resolve in nearby galaxies, less than a parsec from the supermassive black hole, out to the several kiloparsec scales of the galaxy bulge. So this is potentially a conduit for that exchange of mass and energy. Now, in terms of what types of galaxies we're going to be looking at, well, at very, very low redshift, very close to us, there tend to either be not enough or too weak of AGN to study. And as we move to higher redshift, we find more powerful AGN, but they are not as well spatially resolved. So we can't probe the fine scale structure of these mass outflows. So we tend to focus on Seyfert AGN, which are radio quiet, kind of moderate luminosity AGN at relatively low redshifts. Now, the earliest studies from the ground kind of showed that there was some sort of non-rotational motion going on in a lot of these systems, but it was really opened up with observations from the Hubble Space Telescope. And so here's an example of two of the most nearby brightest Seyfert galaxies, NGC 4151 and 1068. And if we take a spectrum of just their innermost regions, we get this very rich set of spectral features. So we have an overarching continuum as a function of wavelength. We also have these narrow forbidden emission line features. We have broad permitted line features, which are coming from the broad line region very close to the supermassive black hole. And we can identify the range of different elements and ionized species that are producing these lines. And in particular, I'll focus a lot today on the oxygen 3 emission line, doubly ionized oxygen, because that tends to be one of the strongest emission lines in the optical. And so this gives us an immense amount of spectral information, but we don't necessarily know exactly where all of this emission is coming from. And so if we return to an image of 4151, here's a ground-based view. We can kind of separate some of the components in terms of the bulge, some spiral arms. But if we go ahead and use the high spatial resolution of HST, we can start to really break down these components into their individual pieces. If we zoom in once more and we use a narrowband filter to isolate that strong oxygen 3 line that's highlighting this hot outflowing gas, we obtain this image. And I really enjoy this image that Judy Schmidt created for us. And so down in the center, we have the supermassive black hole, our source of ionizing photons, which are traveling out, exciting and ionizing this gas and causing it to glow like a neon sign in this kind of bluish whitish hue that we see here. And so we can use this imaging to understand the distribution and the morphology of these outflows. And of course, the second key piece of information is coming from spectroscopy. So in this case, we're using a lot of data from the Space Telescope imaging spectrograph on HST. And if we just had kind of calm, orderly rotation, if we looked at those O3 lines, we might expect just some simple red shifts and blue shifts from each side of the galaxy moving towards and away from us. And that is what we see, but we also see much higher velocity material moving at several hundred to several thousand kilometers per second. And this is that kinematic signature of the outflows, where we have material that's basically being driven away from the supermassive black hole in either direction. So to piece all of this together, here's an animation where we have our supermassive black hole obscuring torus and material. That radiation's traveling out, exciting and ionizing gas within the host galaxy disk, and then driving it away at several hundred to a few thousand kilometers per second. So this is kind of the overall picture that I want you to keep in mind when we're talking about these narrow line region outflows. So with this picture in mind, the big critical question is, how energetic are these outflows? Are they actually powerful enough to have a significant impact on their host galaxy environment? And in addition, before we can even answer that question, we need to understand what the most accurate techniques are for probing these outflow energetics. So in our studies, we've chosen to use cloudy photoionization models to determine the mass of these outflows, with the goal of trying to eliminate as many assumptions as we possibly can about the physical conditions in the gas. Now, the caveat to that is that we require very large spectral range with lots of emission lines, so we focus on just a handful of these Seyfert AGN with the best data. So these are the 6 that I've been studying most recently. They're drawn from a larger study by Travis Fisher in 2013, which essentially looked at a large group of nearby Seyfert galaxies to identify those with these kinematic signatures of outflow. And so this subset of 6 is shown in order of increasing distance. These are all basically Seyfert galaxies and one type 2 quasar, and they're all type 2s without any visible broadline region emission except for NGC 4151. And so these span about a factor of 200 in luminosity, as well as a small range of supermassive black hole mass and Eddington ratio. So I want to walk through our analysis process in just a little bit of detail because it's going to be important later for highlighting what we've learned as in terms of comparing different techniques for determining the mass outflow energetics. So first, for each object, we have an oxygen-3 emission line image shown here by this bright orange image, and we have a STS long slit spectrum. And so first, we extract a spectrum at each location along the narrow line region, for example, with one shown in the upper right here, and we fit multiple Gaussians to the different emission line features that we see. And so in this case, we have a single kinematic component, which is consistent with the rotational velocity of the galaxy. And then we have another offset component, which is consistent with outflowing gas moving at several hundred kilometers per second. And so we do this at each location along the narrow line region, basically as a function of distance from the supermassive black hole. And then we recover the radial velocity profile shown in the upper left here. And so we can see in the example of this galaxy, the velocities increase to some maximum value and then turn over and decrease and basically resume galactic rotation at larger radii. So once we have these fits, we use the fits to the strong O3 line as a template to fit all the other emission lines within our HST spectra. And so this is really what's giving us, it's telling us about the range of physical conditions within the gas, and this is really the key to our modeling process. So the ionization state of the gas, how fried this gas is described by the ionization parameter, by this U. And so it's just the relative number of photons to the number of atoms at the face of the cloud. And so as we increase the ionization, we tend to see higher and higher ionization lines. And so I'm showing an example of this here in the upper right. I can go ahead and change my pointer option. Yes. So basically moving left to right, we're increasing ionization. So we have a larger number of ionizing photons. And then as we move front to back, it's increasing the density, and then the vertical is telling us the strength of that emission line. And so what we see is when we have a very small number of ionizing photons, we basically get no emission. As we start to increase the ionization, we'll start to increase the strength of that line, and eventually it turns over as the gas becomes even more highly ionized, and we get into things like oxygen 5, oxygen 7, things in the X-rays. And so this is really the key to the process, because if we have an estimate of the ionization parameter for a given line, we know how far this material is from the center of the galaxy because the observations are resolved, and we know the luminosity of our AGN. That actually fixes the density. And so it takes this very large parameter space of physical conditions and basically reduces it to a single line. Now, as I said, when we looked at all these spectra, we see a wide variety of lines, from things all the way like neutral oxygen up to iron 14. And so that's giving us a very strong indication that there's a range of ionization parameters or a range of densities within these outflows. And so we typically use up to 3 components, creatively called a high, medium, and low ionization, of different densities, and their emission is mix and match to basically reproduce the overall spectrum. And so here's an example looking at some of the emission lines in the spectrum. And we're looking at basically the model prediction divided by what we actually see. And in this case, a unity would be an exact match, and any deviations from that are telling us that there's some slight bit of physical conditions that we're not accounting for, or there's some modification to atomic data, things like that. So in the end, what this process gives us is the amount of flux that we should expect being emitted from that gas, and the column density, the total amount of gas that we're looking through, and that lets us calculate the mass at each location along the slit. Now, that gives us the mass within the HST slit, and then we use that to scale the entire O3 image up to basically get the mass of this hot outflowing gas. And there are some assumptions about azimuthal symmetry there that I'd be happy to talk about later. So with that, we'll have the gas mass at each location, we have its velocity, and we can use that to calculate these key energetics, such as the mass outflow rate and the energy outflow rate. So without further ado, here are the ionized gas masses for the outflows in these objects. So we're looking at the logarithmic gas mass as a function of distance from the supermassive black hole. And it's important to note that these are not enclosed totals. These are the value at each location. The enclosed total would just rise continuously. And so what we see is that the mass at a given location, as well as the total mass within the outflow, scales with the AGN bolometric luminosity, which are provided in parentheses on the right. And then either at some location they start to turn over because we're basically running out of ionizing photons, or there's more of an abrupt stop, either because the velocities return to rotation or because the depth of the observations is just not enough to carry it on past that. And so for the most part, these are all spiral galaxies except for Markarian 3, which is an S0, and that's being externally fueled by a companion galaxy, which may explain this very sharp rise at small radii. Now, we can take the mass at each location and its velocity and use that to calculate a key quantity that many AGN researchers are interested in, which is the mass outflow rate. And so here we're looking at the rate at which material is being removed by the outflow as a function of radius. And again, we see this trend where both the magnitude of the outflow rate and its peak location are increasing as a function of luminosity. And we see mass outflow rates peaking between about 3 and 12 solar masses per year. Now, that's kind of interesting because it's only about a factor of 4, whereas we're seeing a factor of 200 in luminosity. And where this starts to separate out is if we look at the kinetic energy. And so this is just your simple 1/2 mv squared. And these are not rates, and so these can actually be added up radially to get the entire kinetic energy of the outflow. And here we start to see some separation in the energetics, and that's primarily due to the different peak velocities of the outflows, which are between 500 and 2,000 kilometers a second, as well as just the relative mass distribution. This is not a perfectly homogeneous radial mass distribution. Particularly, you can see some of these large drops at some locations. Finally, we can look at the time derivative of this, which is the kinetic energy flow rate. And this is a quantity that is often used to compare theoretical models and simulations to observations, because simulations suggest that if roughly 0.5% to 5% of the AGN bolometric luminosity can be converted into this energy outflow rate, then we should have kind of very significant or very effective feedback, which can significantly impact the evolution of the host galaxy. And so it's important to keep in mind that those models are also primarily for higher redshift targets that are still building their bulges, but it still gives us kind of a first indication as to the strength of these outflows. And so in these cases, even at their peak, we're seeing something like 0.1% of the bolometric luminosity being converted into outflow energetics. And so we're not quite reaching that threshold. However, a key takeaway here is that we now have a very direct, precise measurement of the amount of energy being deposited into that gas as a function of distance from the supermassive black hole. So taken together, we can go ahead and look at both the gas mass within the outflow and its total kinetic energy on the left, as well as its peak mass outflow rate and peak energy outflow rate on the right. And we can see that in all cases, there's definitely, a scaling trend with bolometric luminosity, but of course, there's not really enough points here to fit a robust slope that we can use over a large range of luminosity space. And so that's something that we're working on at the present time. Most importantly, what we're thinking here is that these multi-component models are giving us very tight constraints on the gas masses and all of these related quantities that are free from a lot of other possible systematics that can be included depending on the assumptions that you make about the physical conditions in the gas. And studies have found that depending on the assumptions you make, you can see scatter on the order of 1 to 3 orders of magnitude, which is very significant if you're trying to compare your observations to these theoretical benchmarks. So this is kind of the main first result of our study, which is these very precise measurements of the ionized gas masses, the outflow rates. And we think these represent kind of the best possible determination that we can make at the present time with our current observations and our current modeling techniques. However, this requires a large wavelength range in terms of your spectroscopy, very high signal to noise, a large number of emission lines, both time and computationally expensive modeling. And so we can really only do this for a few targets. That's why I took an entire dissertation to do those half dozen. And so the question is now, can we simplify this process and still recover kind of equally precise ionized gas masses and outflow rates? So we can measure the velocity of this material and its brightness from spectroscopy of even just a single emission line. And so a big question becomes then, well, what is the density of this gas? And so we wanted to explore a couple of different techniques that are commonly used in the literature. And so the first is to take these multi-component models and just simplify them down to a single component model at a single density. And in addition to that, look at using the recombination equation, which is basically, as I'll show in a minute, just relating the number of photons to the number of atoms. So in the photoionization case, we have the luminosity of some line, in this case of H beta. We have our model predicted flux, and that ratio gives us the area of all of these emitting clouds. And then the model will predict the column density of gas that we're looking through, which is going to give us the total number of particles, so the total mass of that gas. In addition, we have the recombination relation, which is basically just relating the number of photons that we see to the gas mass based on a constant. So it's just photon counting. For every atom at a given density, we get X number of photons per second, and we can relate that directly to the mass. So with all of these different techniques, the key question becomes, what are the gas densities? And so when we used our multi-component models, here I'm showing the results for NGC 4151 on the left, Markarian 78 on the right, because this is one of our lowest luminosity, most nearby targets, and one of our higher luminosity, most distant targets. We can see that we had up to 3 components of different densities and different ionization states. And so we had a high ionization component shown in red, that's matching things like iron 14, neon 5, kind of moving up into that X-ray regime of gas. Then we have a medium ionization in green, and that's matching things like oxygen 3, nitrogen 2. And then we have a low ionization shown in blue, and that's matching lines like sulfur 2, oxygen 1, with all of that emission convolved together to match our spectra. And so kind of a key first observation is that at a given location and as a function of radius, these densities span more than 6 orders of magnitude in some cases. And so we have this very large range of physical conditions present within the outflows. And now we want to go ahead and see if we can simplify this process. And so we wanted to take a look at a variety of different ways of estimating the density. And so a first approximation, if you have very limited spectral information, is just to assume that the density is constant everywhere. And so commonly used values in the literature are 10 to the 2, 10 to the 3, and 10 to the 4 per centimeter cubed. Now, as you can see, there are some
5 minutes left.
Perfect, thank you so much. So in this case, we're just looking at basically a constant density at each radius. The next technique that we investigated is using density-sensitive emission lines. So in this case, using the sulfur-2 doublet ratio to derive the electron density in each case, which is shown here by the gray profiles. And finally, we wanted to look at a variety of power law density profiles, shown here by the solid lines as well as the dashed and dotted. And basically, this is a 1 over r squared law, and I'd be happy to discuss the physical motivation for that, and as well as steeper and shallower deviations from that. And so essentially what we're doing is deriving a power law density based on the ionization parameter. And so in this case, we're using just the O3 and H beta emission line ratio to see if we can kind of get a handle on the density at each radius. So there's a lot baked into these plots here. Again, I just want to highlight that basically we're looking at 3 different ways of estimating the densities: constant densities, those from the sulfur-2 emission lines, and a variety of power law profiles. And so when we go ahead and look at this comparison, first we're looking at just using the recombination equation and assuming constant densities everywhere with our earlier cloudy model results shown in solid black. And what we see is using a constant density of 10 to the 2 shown in red, we tend to very significantly overestimate the gas mass at most radii, more so in our lower luminosity targets and a little bit less so in the higher luminosity targets, but it's still overestimated in all cases. When we go ahead and use the sulfur-2 lines, we see better agreement overall, but we still tend to overestimate the gas mass at small radii because it's underestimating the density. And finally, if we look at using single component photoionization models with those power law density profiles, for example, 1 over r squared shown in green, it works well for some targets, but it still tends to overestimate in some cases because we don't have a really good handle on the column density of this gas. We don't know how optically thick it is. And so finally, we looked at using basically the O3 to H beta ratio to tweak that 1 over r squared profile based on the ionization state of the gas, with those results shown in the long dash orange. And in these cases, we're able to match our multi-component results within factors of about 3 to 5, which is actually pretty encouraging because we're going from multiple components at multiple densities with different dust contents, direct and indirect SCDs, different metallicity contributions, and we're able to reproduce these results. So within factors of a few. So it's encouraging that this technique might hold promise for systems where we don't have such a large wavelength range in our spectroscopy. So with that, in the interest of time, I'll leave my conclusions up. I covered a lot of different pieces today. If I had to highlight one single piece that I think could potentially be the most useful moving forward for a variety of studies, it would be this point here. It's what we're really seeing is that the outflows are not a constant density medium by any means, that we have a very large range in density stratification, both at individual radii and as a function of distance from the supermassive black hole. And so we really need to account for that in some way in order to accurately estimate these mass outflow parameters. So with that, I thank everyone for your time, and I'd be more than happy to take any questions.
Very interesting talk. Let's see if there are questions. I don't see at the moment any raised hand or questions in the chat.
I think that there's someone in
There is a question from, okay, there are two questions. So the first from, oh my God, I lost it. From Yuan Li. You can unmute yourself and ask.
Yeah, that was really interesting talk. I'm wondering if you can estimate the amount of E dot associated with the X-ray gas. Presumably you can't see the X-ray gas, but it's there.
That's a fantastic question. So we do have collaborators working on this at Catholic University, Anna Trinidad Falcao and Steve Kramer. And so, you know, as you probably know, Chandra is an incredible instrument, but except for just a few really nearby galaxies, we can't quite get the spatial resolution of the X-ray observations as we can of the optical gas with HST. And so what we're working on now is using what we call footprint lines. So these are lines that have extremely high ionization potential in the optical and the near infrared, lines that match the ionization potential of, say, O7 and O8, and using those as tracers of the ionized gas kinematics of potentially the X-ray emission line gas. And so they have completed this study for 4151 and 1068. In some cases, it looks like there's about comparable gas mass in the X-ray component as there is in the optical. And in the other case, it looks like there could be up to an order of magnitude more gas mass in the X-ray component. So we still need to expand that out to a larger sample, but at least what we're seeing early on is that it's at least comparable, if not more significant in the X-ray gas phase.
Thank you.
Now we have a question from John Hu.
Hey, thanks, Mitchell. That was a really wonderful talk. So I'm kind of visualizing the picture that you showed in the beginning where you had, you know, like this ionizing bicone, or it was an outflow, but it actually was kind of angled such that, you know, it was impinging on the disk. And so I just had a question regarding, you know, the geometry of these, you know, these systems. Like, is there, well, do you see like a bias, for example, that, you know, like, in terms of outflow or outflow rates, mass loss rates, or even, for example, outflow velocities as a function of like that azimuthal angle there?
Yeah, this is a tricky bit. So in this case, we're looking at a lot of these targets that have kind of this very clear biconical morphology. And what we're seeing now, using particularly more and more IFU studies, is that these most likely represent the most clear cases where that ionizing radiation cone is very clearly intercepting kind of the host galaxy plane. In some cases, particularly more in like the Seyfert-1 galaxies, where things are oriented more in a face-on view, we tend to often see either, you know, kind of a shorter bicone or only one side of the bicone. And there are things you can do to model and deproject those, which we do to try to get kind of the true space velocities. But yes, there is definitely some kind of morphology dependence there. And then in terms of the azimuthal picture, Again, for a handful of these, we have high spatial resolution IFU data. And within kind of the primary ionization cone, which typically contains, say, maybe 3/4 or more of the mass, the velocities are fairly constant at a given radius. Within the cone, they tend to be fairly consistent. But as soon as you go along the minor axis, then that changes dramatically. So as Matilda and a number of collaborators have been working on there, we tend to see much lower velocities there, but the material can still be very turbulent with a very high full width at half max.
Thank you, John. Thank you, Mitchell. I think that there is a question from the library from Raymond Simons. You can ask. I don't hear you.
I saw them unmute, but it looks like there's still a mute on them.
Yeah, they are not. Let's see.
Hello? No. Great. So John actually asked half my question. Can you talk a little bit about the deprojection of the line of sight orientation and I guess how that affects the down the line measurements like the energetics and the densities?
Absolutely. So in all cases, you have to adopt some particular geometry in order to both deproject the distances and the velocities that we observe. And so kind of our earlier models were that this material was actually kind of flowing out along the bicone, which can change basically the relative orientation of that material relative to the host galaxy disk. What we're seeing more now is that it looks like the ionizing cone is lighting up the host galaxy disk and basically driving material along the disk or kind of up and off the disk. That's kind of the clear-cut case in a lot of these. So you can basically use the host galaxy orientation and inclination, which we can get from large-scale continuum imaging, in order to deproject its observed velocity to the true line of sight velocity. But it's not always that clear in a lot of cases, and that's kind of a next step here. Is we have a lot of targets where there's clearly disturbed kinematics, but it's not this very nice clear bicone. And so in those cases, it might be some combination of driving along the disk or driving even perpendicular to the disk, driving off of the disk. And so those are still somewhat of a question mark. But I'd say for the majority of these cases, it seems to be this relatively clear picture where material is being kind of driven along and up off of the disk. And so we can use basically the host galaxy orientation to get a fairly tight constraint on that geometry.
Perfect. We reached the top of the hour, so we have to. We have a last question from Valentina. Hi, Mitchell. Thanks for the nice talk. I was wondering if there is a limit in galaxy mass for galaxies hosting supermassive black holes, and what is the range of galaxy masses in your sample? Also, if there is a correlation between galaxies hosting AGN with measurable outflows with the environment in which they are embedded.
Certainly. Okay. Yeah. A couple of great questions there. So in our case, these are all kind of standard run-of-the-mill, spiral SB type galaxies, except for Markarian 3. I don't have their masses off the top of my head. That is something that I could pull up for you. But I would say they're not, particularly massive or low mass systems. They're kind of very standard intermediate spirals. And for the most part, they tend to be fairly isolated. I mean, these are not void galaxies, but they tend to be relatively isolated. They're not interacting directly with their neighbors, again, except for Markarian 3. And so they tend to be in kind of quiet environments on the whole. I think that handles most of those. In terms of correlations, I would say there's definitely some observed correlations there. For example, if we look in the nearby universe at ULERGs, these ultra-luminous infrared galaxies, those tend to be in merging systems, and you can very quickly funnel a large amount of mass and dust down to the supermassive black hole, and in those cases, we do tend to see very powerful, albeit obscured outflows. So I think that touches most of the points, and I'd be happy to discuss more afterwards.
Thank you, Mitchell. Thank you, Valentina Abril-Melgarejo, for your question. And so it's already 11 and 5 minutes. So I thank you again to Mitchell Revalski and Mireia Montes, that were the speaker of today. And thank you very much to all the people that attended our talks. And see you again in 2 weeks for a next appointment with the Discovery Seminars. Bye, everybody.
Thanks so much for joining, everyone.
Thank you.